In this video I'm going to explain the scalar product or dot product of two vectors, and even just considering this lends itself to the question, how do we multiply two vectors together? So we know how to add and subtract vectors. What do we do when it comes to vector multiplication? And the answer is that there is more than one product between two vectors. So today we're going to consider the scalar product. A couple of things about the scalar product. Firstly, it's an operation which produces a scalar, and hence it's called the scalar product. But typically we call it the dot product because that's the operator symbol that we use rather than a cross like multiplication of two scalar values. So let's have a think about what we might do if we were going to take the product of two vectors. So let's say we had two vectors defined in component form. So A was x1i plus y1j, and then we'll define B as x2i plus y2j. So we're only considering in 2 dimensions in this unit. When we come to 3 dimensions, we can sort of use the same definition. So how would we define taking the product of these two vectors? And I guess there would be a whole lot of ways that we could choose to do that. And so mathematicians have chosen a couple of different ways to take the product. And the scalar product is defined in the following way. A dot B, and as I said, the dot is the operator symbol for the scalar product. A dot B is equal to x1 times x2 plus y1 times y2. Alright, so that's a definition of the scalar product there in component form, and we'll consider that there is another form of that as well. But before we go on to that, let's actually just think about what that looks like when we take the scalar product. So if I was using that definition there for an example, I'll just define two vectors A and B. So we'll say A is 3i plus 5j, and let's define B as negative I plus 9j. Then the scalar product or dot product of A and B, and notice we don't use the multiplication symbol because that means something completely different with vectors. Let me write them in sort of column form here. So 3, 5 dot negative 1, 9, and in column form it's really easy to sort of read off the scalar product because I'm saying it's the product of the I components or the x values there. So that would be 3 times negative 1, and then it's going to be the product of the j or y components there. So that's 5 times 9. So negative 3 plus, what's that, 45. So that's going to be equal to 42. Now, that's how we operate using that definition there. But the other thing I want you to notice here is that we end up with a scalar. Okay, so we started off with two vectors, and when we take the scalar product, we end up with a scalar, and hence the name. Alright, let's think about a specific situation in this example. What if we were to take the dot product of A with itself, or the scalar product of A with itself? So that would be, what is it, 3, 5 dot 3, 5. And so what we'd actually end up with is 3 squared plus 5 squared. And so what's that? 9 plus 25 is 34. Now the reason I put that example down is that I want you to think about, and maybe if you use this line here, you can see that in fact that is just like the magnitude of A without the square root symbol. So in other words, that is the magnitude of A squared. Okay, so take a moment to think about what the magnitude of A would be and how we calculate that, and hopefully then you can see that that there represents actually the magnitude of A squared. Now that leads us to a few, or the first of perhaps our useful results. And I should say here that defining the dot product or the scalar product in this way actually has a whole heap of uses. And really that's sort of how we do things in maths, isn't it? We define operations in a certain way because they have a whole lot of uses. If you think of defining multiplication in the way that it's defined, that's a really useful operation to have. Alright, so the first of our useful results or important results is the one that we just showed there, which is that the dot product of any vector with itself is just equal to the square of its own magnitude. The second one, which hopefully you could see fairly easily if you sort of reverse the order of A and B, is that the dot product, the scalar product, is commutative. Don't know if you remember that word, but remember that means if we switch the order of the inputs in our operation, then it makes no difference to the answer. So reversing the inputs here makes no difference. And the last one is to say that if we had, so if we were taking a scalar times vector A and then doing the dot product with B, that would be the same as just going A dot B first of all and then multiplying the scalar, or even saying A times, or not A times, A dot KB. So where we multiply by the scalar in that result doesn't matter. Alright, we've got a definition for the scalar product in component form. Let's go on to a definition in sort of geometric form, or I guess when we're considering polar form, where we've got a magnitude and direction. Alright, so our geometric definition, if we have two vectors A and B where we know the angle between them, so let's say there's vector A, there's vector B, and there's an angle of theta between them, then the geometric definition of the scalar product A dot B is that it's the magnitude of A times the magnitude of B times the cosine of the angle between them. Put a little box around that one. Alright, so magnitude of A times magnitude of B times the angle between them. Now again, hopefully you can see that that's going to result in a scalar value. So the magnitudes are both scalars and the cosine of the angle is also a scalar value. So we're multiplying three scalar values together, which is going to produce a scalar. Now why does that produce the same result as the component definition? Well, in this video I don't have time to explain that, but I'll make another video where I just kind of show that those are equivalent expressions for the scalar product. You don't need to know that, but you might be interested in that. So let's do an example in this form here. So if we had two vectors defined in polar form, so let's say I had a vector u which has a magnitude of 3 and direction of 28, and then let's say this one here, v, can be that, and let's make it a negative angle there. Now the only thing we really need, we're given the magnitudes of u and v there, the only thing we just need to consider a bit carefully is what is the angle between them. And it might be helpful to just quickly sketch for yourself and say, well, one's at positive 28, so that's 28 degrees from the positive horizontal. The other one's negative 105, so I guess it's kind of down in that direction there. So it's 105 degrees down that way. So if we were to calculate the total angle between them, in this case we would just need to add those together, wouldn't we? So 28 plus 105, which is, what's that, 130. Well, I'm not sure what happened there, I just suddenly lost connection. But anyway, we were saying that the total angle 28 plus 105 is 133, and so therefore we could say u dot v is going to be equal to magnitude of u times magnitude of v times the cosine of, let me just say first of all cosine of theta. So the magnitude of u we're given is 3, magnitude of v we're given as 8, and we said the angle between them is going to be 133 degrees. So I guess just need to grab our calculator there, work out 3 times 8 is 24, times the cosine of 133 is going to be negative 16 not degrees, negative 16.87, no, sorry, negative 16.37, let me just get that right, so 0.37. So again, it's a scalar value. Notice in this case it's negative, so you might ponder what is it that makes that negative, and then think about why can the scalar product sometimes be negative and sometimes be positive. Alright, in the next video I'll just do a really quick example of one of the really useful uses of the scalar product, and then I said I'd also make one to explain how the geometric and component definitions are similar or come from the same result.